Hi, in this video, I'm going to show you how to calculate a margin of error. Two examples I'm going to cover is the margin of error for a mean and the margin of error for a sample proportion. So let's cover the margin of error for a mean first. So let's say in this situation you have a bar and you want to know what the average ounces are poured for shots of whiskey for your bartender. So you take a random sample of 50 in one night. You have a very popular bar. And you kind of want to find out what is the average ounces that are poured plus or minus some amount. So that's your margin of error. One way we can do this is we have our 50 here. So I selected my 50. It says count 51 because I have my label here. But I can bring in something called the data analysis tool and bring in the descriptive statistics there. I'll show you another way to do it with the formulas, but this is probably the easiest way to do it. Data analysis is an add-on that you have to put into Microsoft Excel. If you don't have it in there, just Google data analysis add-on install Microsoft, and it will show you how to do it. You'll probably find some websites to show you how to do it. But since it's here, I'll go ahead and click on that, click on descriptive statistics, click OK. My input range is A, column A. Well, let's just make it more specific. A1 to control shift down arrow to select it all to A51. Let's go back up here. And it's grouped by columns. It's one column. There is a label in the first row. My output range D5. Do I want it in D5? Yeah, let's D5 is fine. And I want summary statistics and I want this confidence level for the mean. Click OK and it's going to put it there. And pretty much my work is done. Let's double click this to auto fit. My lower bound and my upper bound, I'll show you how you get to it. So basically my lower bound is my mean minus my confidence level here, and the upper bound is the mean plus the confidence level here. Let's make this a little bit smaller, reduce the decimals. Well, let's just go to the hundredths decimal. So what this is saying, I'm going to move this thing over here. What this is saying is that my average ounces poured is 154, so that's 154 with a margin of error of plus or minus 8. That's that over there, right? So if I hired a new bartender and that person was pouring a little bit more, 1.75, then she'd be pouring too much whiskey, although the customers probably would not mind. Now, there are other ways that we can calculate this. If you didn't want to be so lazy and have it Excel calculate for you, you can actually find functions to calculate all of this for you. And I'll show the functions here. Right? And so we have our average. It's using the average function. You can see that basically this cell here is just telling you what formula it's using. So our average 154, which coincides with that. Our standard deviation formula is the standard dev. Let me double click that to auto fit that. Standard dev.s 0.28, which aligns to the standard deviation here. And the reason why we're using standard dev.s is because this is a sample. We're not assuming that this is the whole population of all the bartenders in the world. We're just using a sample. So that's why you have standard dev.s. You notice that if I click on here and I delete this s, it'll give me options for a P or an S. So we're going to use the S one because that it's just a sample. It's a smaller subset or a sample of a population. Standard error, I'll cover this a little bit more when I get into the t-scores. The margin of error that we found is the same that we get from our confidence level. That is our margin of error at a 95% confidence level. So why are we using this particular function, confidence.t? This is using the t-score. Now the t-score is basically used if you don't know the population variance or standard deviation and or the sample size is low, usually around, the guidelines are around 30. So we have a count about 50. Even though this is not 30, it is lower than what you would probably normally see before you can use a normal distribution, which would be the z-score. So what does a t-score look like? Well, we're going to take that from the t-distribution table. So you can see here, you're probably familiar with a z-distribution table. I'll show this one a little bit later, and a t-distribution table. So with a t-distribution table, as I said before, basically use this if you don't know the population variance and standard deviation, and or the sample size is low. You'll notice that if I go here to it, we are looking at a 95% confidence level. So there's different confidence level. You can say, oh, I'm 80% confident, or I'm 90% confident, or I'm 95% confident. So it just depends what you want to say. Now, usually with 95% confident, that's 2 standard deviations from the mean. So that's 1 standard deviation, 2 standard deviations going both ways, the negative and the positive. So 95% is the area in this under the curve. Anything outside of it are the tails. That's called your alpha. So with a 2-tail confidence, that's 95%, which encompasses this area. And outside of that is your alpha, which is 5%. Since we have 2 tails, basically it's that 5% divided by 2. So each side is 0.025. You can see that it states it here. Now, if you're just doing a 1-tail alpha, you can see it's 0.025. If you're including both tails, it's just basically double that. So we are looking at our 95% confidence rating, and where are we going to get our z-score? Well, this area is going to be telling us how many samples that we have. If I scroll all the way down, you can see it kind of stops at around 30, right? So this is kind of with this table. Other tables can show you higher amounts to 50 to 100. If we go to another table here, let's see if we can find another table here that has a higher one. It will tell us that if it gets too large, you can see if it gets too large, it gets to 1.96. And 1.96 is basically the same score as a z-score. And just remember that number, 1.96 at a 95% confidence rating, right? Let's get back to our particular example here. So our confidence here is 0.05. Remember we had the 2 tails? That's why we have that 0.05 there. So the formula says, give me the confidence of the t table from the t's table of 0.05. I6 is my standard deviation, and 50 is the count. So that's where we get our margin of error. That's how Excel is calculating it here. And that's where we get that 95% confidence level. Now, that's the way we can calculate it here. So if I wanted to find my t-score, just using Excel, you can see that there are 2 functions for that. One called the t.inv for a 1-tail t-score, and the t.inv.2t for the 2-tail. So these output the same number, but you can see that it's asking for different arguments. So the t-score here for our 95% confidence, for a sample of 50, you can see it comes out to 2.01. Right, so if we go back to a t-table, let's bring up a t-table that's kind of close to that. Find one. This is between 30 and 60, right? So if we look at a 2-tail test, 0.05 is our alpha. It's going to be between 2 and 2.042, which is pretty close to the value that we got here, right? 2 and 2.04, I believe, 2 to 2.042. Yep. So that's pretty close here. So our t-score here tells us that. Now, to get our margin of error from those t-scores, all you need to do is just multiply that t-score times the standard error. This I7 is my standard error that I got here. And the standard error is basically your sample standard deviation divided by the square root of the count. That particular formula is this one, right? We were going to look for our standard error. That's our standard deviation, this divided by the square root of the sample size. Now, since we don't have the population, this sigma should be an S. So it's the standard error for a sample, not a population. But this one is showing you the standard error for a population. Now going back to Excel, that's how we do it. So this basically gives you the same thing, right? You have your 0.08, your plus or minus 0.08 from the average, 154, which what we're saying down here. So that's how you would find a margin of error. There's a couple ways you can do it. You can use the data analysis feature to kind of just, that's the easiest way. You can just kind of bring it in and you get your average plus or minus your confidence level of 95%. The other way to do it is to figure out your average and your standard deviation and then put that into your confidence function, your confidence T function to get your margin of error, and then that is your plus or minus from the average. A third way is to get your t-scores. You can either get your t-scores from a table or get your t-scores with the t.inv or a t.inv2t function. And once you have your t-scores, then you would multiply that, one of those, you can get your t-score and multiply it by the standard error, which is that function. I actually should probably bring this particular formula down here because it more or less applies in this section. Because all you need to do to get your margin of error from these two, and to get your margin of error, you need to get t-score from here and multiply it by the standard error. So that's how we can do it for a mean. Now, if we wanted to do it for a proportion, that tries to answer a different question. So in proportion, let's say there's about 50,000 people in a company, and you want to find out if the employees think that the CEO is doing a good job. You pull about 900 of them. You don't want to pull all 50,000 of them. You pull about 900 of them in your company to try to get the results. And this basically brings up the idea of the standard error of the sample proportion. So to get that, what we want to do is we want to have this function where we have p multiplied by 1 minus p over n and find the square root of that. So to basically get that, what we need to do is we kind of need to tabulate this all. So I have this particular data. I'm going to turn it into a pivot table, insert pivot table, and I'm going to have it on the same worksheet here. Let's put it in C4, click OK. And what I want to do is I want to have a count of the good jobs versus bad jobs, the yeses and nos, right? So we have 900 in total of our people survey. It says 901 because I have the label here. And I want to get a percentage of that. So to get a percentage of that, I can also just put this in there twice. And instead of having that count, I'll click on the drop down, value field settings, and I want to show values. Whoops, let's not do it on this one. We want to do it on the second one. Also here, I don't need to go down to the drop down here. I can go right click. And then show values as a percentage of the column total. Right, so this is 52% or 53%, and that's 44%. Let's not do the decimal places. Right click, value field settings, and our number format, let's do percentage, but we don't need the decimals. Click OK, click OK, and now we have 53 versus 47%. I'm going to close this now. And what we can do here is we want to figure out the standard error. So to figure out the standard error, what we need to do is put the numbers here. So P is going to be our yes, 47. So I've got my data here that says 47% of the people surveyed say the CEO is doing a good job. But what's my error? What's my margin of error? So how do we figure that out? What we need to do is we need to find the standard error of proportion here. So to find out the standard error of my sample proportion, this shows it. We have the standard error for proportion here. It's basically the square root of p times 1 minus p over n. Now if I go back to my worksheet here, p is my 47%. So that is going to equal the square root, and I put that in open parentheses, of 47%, 0.47 times 1 minus 0.47, close parentheses, and that's basically going to be 53, right? 100% minus 47% is 53%, 0.53, so that's basically what it's saying. And we want to divide this by the sample size, which is 900. Close parentheses, press enter, and I'll just label the standard error. And this is the standard error of the population proportion. Let me put the formula text here so you can see the formula. Right? So that's that formula for that. And that's basically the standard error formula. Now, usually in these kind of polls or surveys, you usually see 95% confident. And so when we say 95% confident, we're talking about using a z distribution for this particular sample, because usually a z distribution, you're kind of assuming that you know the standard distribution and also the sample size, and or the sample size is large. In this case, it is large, about 900. So what we want to do is we want to multiply our standard error. We want to multiply the standard error by a z-score. So to find out the z-score, we need to find out what the z-score is for the 95% confidence. So let me go click on here. And for a normal distribution, what we're assuming for a normal distribution is 95% is within this red range, and on the outside of the tails is 0.25 respectively for each tail. So that would be 0.05, so that's 5% there. And when we're looking that up in a z-score table, usually most of the z-score tables that you find are one-tail tables. So you're going to have to look up the alpha for that. You're looking up the one tail. So you're going to be looking at 1 minus the alpha divided by 2, right? This is alpha, but 2.5 is alpha divided by 2. So in some tables, you're either going to look for this 2.5% or the decimal of 0.025, or you're going to be looking at 1 minus 0.025, which is 0.975. In this particular table, it gives us the 0.025. So if I go down here and I'm trying to find 0.025, you can see it's the intersection between 1.96, right? And that's what it's doing. It's giving us the left tail, 1.96. So that's the z-score that we find. So if we plug in 1.96, that's 2 standard deviations from the mean, right? You can see that it's 2 standard deviations to the left and it's 2 standard deviations from the right. That is what gives us our 95% confidence, right? We're saying that that value is, we're 95% confident it's within that normal distribution under that bell curve there. So now I want to find my margin of error. So what I need to do is I'll just have my 1.96 multiply, 1.96 multiply by my standard error, and that's going to give me my margin error. So my lower bound will be my 47%. It will equal 0.47 minus my margin of error here, and the upper bound is going to equal 0.47 plus my margin of error here. And I will make these both percentages. And basically what we're saying here is that we are 95% confident that 47% of our employees think the CEO is doing a good job, plus or minus 3.2%, right? That's where our 44 and 50% come from, that plus and minus. So that's what we're saying. Now, incidentally, if we didn't have a z distribution table available for us, we didn't have internet access to go and find it, we can actually look it up with some formulas. Now, let me press escape here. And the formula that we can find it is with the norm S inverse formula. So the probability that we're trying to figure out here, so this is going to give us a one-tailed score. So instead of putting 0.05, we need to kind of do the inverse of that. And that gives us 0.025, but we have to use the inverse of the alpha, which is, when you think of 1 minus 0.025, that is 0.975. Close parentheses, press enter, and there we have our 1.96, even though it's out there to the many decimal places. So that is how we find out our z-score using the formula. I bring in my formula text here. That is our formula here. Go to F2, F14 there. Our norm S, I, and V gives us our z-score. So that's basically a side note of how we can get our z-score using a function. But if you had our table, then you can just plug it in to our standard error number, which we got from this particular formula. So that's how we can get a margin of error for a sample mean and a sample proportion. So I hope that helps. Thanks for watching.